It's time to tackle the intermediate value theorem, and this is another theorem that falls into that family of what we call existence theorems. And so we'll put a special note of that somewhere here in our notebook. It's an existence theorem. The other theorems that we're going to put into that family are the extreme value theorem, that basically proves there's a relative or an absolute max and min within a closed interval for all continuous functions. And then we've also got the mean value theorem, which is probably the granddaddy of them all. And tonight we're going to add the intermediate value theorem and go over it in great detail. And I think this is a very simple one. And I think this little graphic here tells you the whole story. Not only do we have the formal definition here, but we got a great visual for you to sort yourself through. And as you're copying this down, take a moment, just take a deep breath, read through it, and then I'll try to translate some of the verbiage for you. The first thing that I noticed is this monster prerequisite, and this is the only prerequisite we have to worry about tonight. In order for the IVT, the intermediate value theorem, to be applicable, f has to be continuous. That's it. We don't care if f is differentiable tonight or not, and it's got to be continuous on the closed interval from a to b. This capital letter N represents a y-coordinate that falls between f of a and f of b, which again, f of a represents the y-coordinate at x equals a, and f of b represents the y-coordinate at x equals b. And we are going to assume that f of a is not equal to f of b. If that's the case, then there has to be a number we'll call c, and that's an x value that falls between a and b, can't equal a, can't equal b, such that f of c equals n. And I think this picture tells it all. So to get from point f of a to point f of b, somewhere on my travels, I've got to pass through n. Whether I do it real early or whether I delay that, sometime I've got to pass through a y-coordinate of n. I think the best thing about the IVT is it really passes the common sense test, and we certainly don't want to make it any more complicated than it is, although the verbiage that we just dealt with in that formal definition can be a little overwhelming. So for beginners, what if I told you that f of 2 was equal to 6, and I told you f of 5 was equal to 10? Then basically what we're saying is, and we'll try to visualize this graphically, maybe here's 2 comma 6, and then a little while down the road, we've got 5 comma 10. And basically, could you try to prove to me that this continuous function f has to pass through, say, is there a point where the curve would equal, say, 9? And I think no matter how you try to connect these two dots, whether you draw it like this, or like that, or come around this way, or maybe you try to shoot up and down, no matter how you try to get from point A to point B, at some point you're going to pass through a point such that the y-coordinate is 9. So we could guarantee that there is a value c, again now c is an x value, that lies between 2 and 5 such that f of c would equal 9 by the intermediate value theorem. Another common sense example that we could kind of put it in context with is pretend that maybe you've got Easy Pass and you're driving your car, and typically when you're driving along the thruway, your velocity is a continuous function. You might speed up at times, you might slow down at times, but your velocity is a continuous function. And as I went through the Easy Pass, we'll say that's where I started my clock, and I would say my velocity at t equals 0 at the moment I went through Easy Pass was maybe 15 miles per hour. Now a minute later, we'll say t is measured in minutes, v of 1, I've accelerated up to the speed limit and I'm cruising at 65 miles an hour, because we'd never ever dream of going over that. So here's the trick. Was there ever a moment where I was driving 50 miles an hour? Okay? Think about that. Was there ever a moment where I was driving 50 miles an hour? Even for a split second. And I say absolutely, because as I was accelerating from 15 up to 65, at some point between t equals 0 and t equals 1, my velocity must have been 50 miles an hour, at least for a split second, if not longer. So here's a real life problem to sink our teeth into, and this is taken out of a pre-calc textbook. And this is generally a theorem that's first introduced in pre-calc and then maybe extended and refined a little bit in AP Calculus. And we'll see some really wild applications of it before the video is over. But they want us to use the IVT to show that this polynomial function has a 0 somewhere between x equals 0 and x equals 1. Now notice, this is significant that it's a polynomial, and it's part of the reason it's a polynomial is because all the exponents I have are whole numbers, positive whole numbers. And so what that does is it guarantees, because it's a polynomial, it guarantees that the function f of x is continuous. And that's really, really crucial because we want to establish that right away. We know that f of x is continuous now, which then makes the IVT applicable. And we do want to declare that on any test or anything that we do in class. We want to declare that f is continuous and therefore the IVT is applicable. Remember, today we're not worried about whether f is differentiable or not. So the first thing I want to do is I want to evaluate f of 0. And by substituting a 0, I ended up getting negative 1. And I'm going to evaluate positive 1. And let's see, 1 plus 2, let's see, that looks like a 2. Notice, one of the numbers is less than 0, the other one's greater than 0. So we could say that this function, by the time it travels from negative 1 to positive 2, must pass through 0 at some point. And here's how I might justify this if I was showing all my work on a short answer. I might say of course, after I've declared f is continuous and so forth, I would say, well, because f of 0 is equal to negative 1, and that's less than 0, which is then less than 2, which was equal to f of 1, then by the intermediate value theorem, there must exist a value c. And now we want to declare where that c lies real quick, and we're going to say somewhere between 0 and 1. There must exist a c between 0 and 1 such that f of c equals 0. And again, you get a feel for why we call it an existence theorem. The intermediate value theorem didn't actually help us identify the value of c. It just guarantees that it does exist somewhere between 0 and 1. We're going to wrap up tonight's video with an actual AP question from the 2014 exam. And feel free to pause here to try to digest some of the given information and just familiarize yourself with it. But the gist we've got here is we've got a train. Train A runs back and forth on an east-west section of a railroad track. And train A's velocity, which was measured in meters per minute, and it's given by a differentiable function v of a. Now that's special right there. I'm going to come back to that in a second, where t is measured in minutes. Selected values for velocity are given in the table above. So at t equals 0, the velocity of the train was 0. In other words, it wasn't moving yet. 2 minutes later, it was traveling at 100 meters per minute. Yeah, etc., etc. Now the negative velocity just means it's heading left, or probably in this case west. It's just remember, velocity is directional, so we can think of positive velocities as moving forward, negative velocities as moving backwards, basically. And part B of the question says, or asks us, do the data in the table support the conclusion that train's A velocity was negative 100 meters per second at some time within the interval 5 to 8? And so this is an existence style question. We're not actually trying to find the value of t, we're just trying to prove whether it exists or not. And it's a perfect example of the intermediate value theorem. And first thing we want to declare is, let's go back and underline this part of the question right here. The fact that the v of a function was differentiable, okay, implies that v of a is also continuous. Now remember, differentiability does imply continuity, but that's only a one-way street. Continuity would not have implied differentiability if it was the other way around. Okay? And the next thing you want to notice is maybe we'll put brackets, and let's go with a little fatter pen style here. Right in between here, let's bracket that little interval. And you'll notice how the train's going from a velocity of 40, and then 3 minutes later, the velocity is negative 120. So somewhere on the way from 40 to negative 120, the velocity must have been negative 100. And I think that's, for the most part, that's just a lot of common sense right there. And we could see that happening in real life almost every day. Maybe not with a train, but something similar. So what I'm going to do now is I'm going to say something like, well, the velocity at t equals 8 was negative 120. That happens to be less than 100, which just happens to be less than 40, which was the velocity of train A at t equals 5. So I always want to take the value I'm trying to prove and sandwich it in between two given values, okay? We're going to sandwich it right in there. Now we can just kind of wrap it up with a little conclusion statement. We're thinking, therefore, by the intermediate value theorem, there is a t value. There is a t somewhere between 5 and 8 such that the velocity of train A at that t value is equal to negative 100. Again, it's an existence theorem. We don't know exactly what the value of t is. It might be, for all we know, it might be at t equals 6 or t equals 7 or maybe 6.8 or something like that. But we do know that it does exist.